Great, thanks a lot. So thanks a lot for coming. Thanks a lot for having me. I already told Daniel that I'm enjoying this a lot. Oh, it's not optimal. Okay. Let's see. Yeah, not optimal. This is also, I mean, we never shoot for optimal here. Approximate is fine. Okay, this is joint work with my friends from the Netherlands. Daniel is here, Sophie is here, Christopher is, I guess, in Eindhoven. All right, and it's about speeding up the cutting plane method. Everything what I will say, and I'll make some comments later, will also make sense without the cutting plane method, but it helps for the story today. So we will talk about some algorithms that all have their own meaning on their own, but inside the cutting plane method, I think they're even nicer. Good. So what is the setting? So the setting is we want to let's say we maximize a linear function over a convex body, and that convex body is only given by a separation oracle. Okay, so I guess most of you are familiar with that setting. We have many interesting applications in combinatorial optimization. Yesterday in Andreas' talk, we saw some applications where the separation oracle deals with semi-definiteness constraints. People have some nice applications in machine learning. We will see them later, actually. Okay, so just that we're all on the same page. So what is that separation oracle? What you can do is you can take any point in R to the D. The microphone is too close. Oh, too close. Okay, fine. That's easy. Yeah, I see. Yeah. Great. So what you can do is you can take any point in R to the D, and you can ask the oracle about that point, and the oracle might say, yes, that point is inside the convex set C. And otherwise, it will say no, and it will even provide you with a linear inequality that we always encode as A comma B, where the inequality is of the form A transpose Y lesser equal E, and it's set B, and it's satisfied by all the points in C, and it's violated by our point X, right? So it's a standard setting. I guess you all know that setting. Good. So we will make some just technical assumptions. Let's assume that this objective vector has norm 1, fine. Let's assume that our convex set sits inside a ball of radius capital R. And let's assume our set is also not too small, so it contains a ball of radius little r, but the center of this, like the big ball has center at the origin, the small ball has its center somewhere, and we don't know it. So in particular, we do not necessarily know a feasible solution, okay, the beginning. Good. I mean, how do you deal with that problem in practice? I guess we saw it yesterday. It's a very natural approach. You run the standard cutting plane method. So what does it mean? You start with some initial constraints, a finite number of initial constraints. So it's going to be, let's say it's going to be a polytope. Okay, and then what do you do? Well, there is an obvious linear program that you can solve. You do that, you obtain an optimal solution, and that's the point that you use to query the oracle with. So that's the point X star, right? So you ask the oracle, in this case, if this point is feasible, you're done. If not, you get a violated inequality, you add it to your system, and you repeat that whole process, okay? And here in this talk, so yesterday, Andrea was really talking about like which of these cuts should we really take and so on. So in this talk, we assume that this oracle is really a black box for us. It gives us any cut. It could even give us a very nasty cut that just chops off our solution very badly. Okay, so let's not assume anything about this. Good. So standard cutting plane method, we all know it, I guess. It is a very nice procedure, right? It's very simple. Very often in practice, this just works, okay? Maybe not, we've seen yesterday, maybe not for semi-definite programs, but I mean, in many cases, this just works. And also, like we learned it even a day before, like in this talk here, we just add one cutting plane in every iteration. And in this case, this cutting plane method, it can quickly update. And in particular, what we get in every iteration is, what you always get is a dual bound, okay? You always get a dual bound, in this case, an upper bound on your problem. So this is all stuff that we want to keep. I mean, there is no complaints about this, okay? So this is fine, okay? It's totally fine. However, there are some small downsides. So first of all, for this method, you cannot give any theoretical guarantee. Just as I told you, I mean, if the oracle is very nasty, you make almost zero progress, right? So, okay, fine. And also what I personally don't like about this method is you don't have any intermediate bounds. You don't encounter any intermediate primal solutions if you just do this, okay? You only have a primal solution at the very end, okay? Which is, okay, that's maybe not great, okay? Good. So today we would like to talk about, some variation of the cutting plane method where, we want to keep this, but we also would like to have this maybe. Okay. So how can we do this? Well, what's the degree of freedom? I don't want to change much. The only thing that I want to do is maybe let's use another point for querying the oracle. Okay. I mean, this point x star is a natural point, but let's do something else. Okay. So maybe just to get the setting right, and please ask me if you don't understand anything. So what we do is we still start with some initial constraints. During that process, I would like to keep a lower bound. So let's start with some very stupid lower bound. Maybe, objective has norm 1. So maybe a lower bound is minus r. Okay, so start with some lower bound. Then we will always solve that LP. That's fine. I mean, I told you it's cheap. So this LP, we don't care about the point that where C is currently maximized, but the LP certainly gives us an upper bound. And if we run that process, I guess we want to stop whenever the gap, like here we talk about an additive gap, whenever the gap is small. Fine. Now here's the point. Now we want to have some flexibility on what is the next point x star that we want to query the oracle with. Okay. And I will tell you about some interesting options. And then you do the standard stuff. I mean, if it turns out that x star is feasible, I mean, you're not done. I mean, it could be any point, but you certainly can check whether it improves your lower bound. Maybe it gives you a better solution. And if not, you get a cut, you add it to your LP, and then you repeat. That's it. So the only thing that I want to change is this. Is that clear? Good, good. So what can we do? Well, remember we're in the oracle setting. So what is the first algorithm that comes to your mind when you're in the oracle setting? Well, I think about the ellipsoid method. So let's do it. Does it make sense in that setting? Well, what's the ellipsoid method? Well, you should start with some initial ellipsoid. Well, that's natural in our case. Maybe we take this capital R ball. Okay. And then you maintain that ellipsoid during that algorithm. Okay. And once you maintain these ellipsoids, so what's the point x star that you should query the oracle with? Well, that's the ellipsoid story. You take the middle, the center of the ellipsoid, you query it, and then you update. Okay. Now, what happens if you get a cut? Right, you might get a cut if your point is not feasible. So you update your ellipsoid as usual. So that's the typical thing. Now here we're like typically this ellipsoid method is only taught in this feasibility version. So here we want to optimize, and I don't want to do any binary search, right? So there is actually an optimization version of the ellipsoid method, which makes sense. So what you can do is, like, if your point turns out to be feasible, usually in the textbooks you stop, right, and you repeat with some binary search. Here, one thing that you can do is you just take that objective cutoff. You treat this objective cutoff as a constraint. You just write down C transpose X is greater or equal than the current objective value, add it. And then, I mean, you treat it as a cut. So the ellipsoid will always take care of the optimal region, okay? So can be sure the optimal region is contained. You just do this and it still works out nicely. It's basically the same analysis. So what happens is, I mean, now you have some theoretical bound. So after, like, if you want an epsilon error, you achieve this after at most this many iterations, okay? And this is in some sense great, right? Because, I mean, you all know that, right? I mean, 1 over epsilon is in the logarithm and blah, blah, blah. Maybe one thing that you might not like is this dimension, factor of dimension, but I mean, it's okay, okay? Oh, maybe it's a d squared. Okay, sorry, yes. That sounds strange. Yeah, it's a bit. It should, you have an R and an epsilon in the bottom. So if you rescale everything, I would expect an R squared in the top. Sure. I mean, yeah. Right. Yeah, there's an O. I agree. Yes, I agree. Yes. So it's like this, right? So this is very good if you want to shoot for very small errors, but I guess most of you know this is only good in the long run. So it turns out that in practice, this method is really slow. And we will also see later experiments. I mean, this is really true. It's very slow, okay? So it's not perfect. And by the way, so when I talk here about iterations, it's really a big iteration. Like, it's basically an oracle call. So this is what I measure, okay? Good. So there is another method, and we heard about this method in one previous talk. I don't know if you know it. I didn't know it before. It's the analytic center cutting plane method. So this is another famous way of dealing with this separation oracle setting. It's very easy. So here, this point x star arises from a simple computation. What you do is you take all the constraints that you have learned so far, plus this objective cutoff again. You also treat it as a constraint. So this gives you a polytope. And you compute the analytic center of that polytope. And the analytic center is just the maximizer of this function, which we all know it's a strictly concave function. So you do this, okay? And I mean, you don't need the exact maximizer, but this. So this is a well-known method. You also have some theoretical guarantees. I'm sorry if, again, the exponents do not work out. Now we don't have a log, but my impression was that this should be the right thing. Although here the story is a bit less clear. What you definitely also have is a dependence on the dimension. Okay, and yeah, again, you don't have a log around, so this is a bit worse, of course. But actually, this method, we have implemented it again. It works in practice. It works in practice, and actually, it works pretty well, at least for the dual side. So it turns out that this method, at least in our experience, like the cuts that are generated by this method, they are pretty strong for the dual bound side. Now also, but however, in this framework, right? I mean, this method, it can also create some feasible points in between, which bring our lower bound up. On the lower bound side, this method still seems a bit weak. I mean, we will see it later, okay? So in this talk, I would like to talk about a new or another method that we came up with, which works as follows. So here, yes. Can you just repeat?
I believe there are ways to get a log to the analytic center.
Oh, interesting. Okay. Oh. Okay. Yeah, Aaron just mentioned that it seems that you can get the log into the dependence on capital R and little r and the error by paying a bit on some polylog in the dimension. Yeah. I have to, okay. Oh, I have to add and drop constraints. Okay, it's not that straightforward. Yeah. Yeah, I must admit that the literature, at least for me, was not that straightforward on that method. Good. So here's so that's okay. Maybe we don't like the dimension too much. And yeah, that's okay, but maybe you can get it a bit better. So here's our method. I think in order to have the formulas correct, we assume that every constraint vector has a left-hand side that is norm to 1. Whenever I talk about the norm, it's Euclidean norm, by the way. So what we do is the following, and then I will later tell you why this makes sense, I guess, is that we treat all these constraint vectors as points, like in the homogenized space. So we add the right-hand side as a coordinate. We also divide it by capital R for some normalization. You should not care about this. We also treat this guy, again, like C transpose X is greater or equal than the lower bound as such a point, okay? And we take these points. Now we consider the convex hull of these points, so that's a polytope. And inside that polytope, we want to compute the minimum norm point in that polytope, okay? It turns you don't need the minimum norm point. You'd like just some point with small norm, but we will see this. Okay, so this is a point that we compute. So what's the point x star that we should use for the oracle? That's almost the point P. What we do is we take the first dimension many entries, and then we normalize by the last entry and capital R. Okay, and we will see in a minute why this is the right point that you want to get. Good. All right. So and what we can prove about this method is that after this many iterations, you can get an additive epsilon error. I would say this is pretty comparable to what, for instance, multiplicative weights can achieve, I would say. But it turns out that in practice, this method is in all the tests that we did is pretty comparable to the standard cutting plane method, and in several instances even better, even much better. Okay, we will see this. Good. So, but before we go to the computational results, so let's go to what is the idea behind this? So why does it work? And it's pretty simple. So maybe for the analysis, let's say that capital R is 1. Okay, so then we really want to compute or a point of small norm in the convex hull of these nice vectors. Okay. Now the first claim that I make is that if you really have found a point of small norm in that convex hull, this really means that your gap is small. And then maybe you already have an intuition why this is the case. I mean, the first small observation that you make, and this is an easy exercise, is that I mean, we contain a small R ball, and if you use that fact, then you can show that if you really want to get the norm very small, you cannot put all the weight onto these coefficient vectors. There must be some, like this vector must have a positive coefficient. Like you can also give a lower bound on that coefficient, because that inner R ball point will produce a certain slack here. It cannot work. Okay. So in particular, this means that, I mean, suppose you found a point of zero norm, so you found the origin in that convex hull, then that simply means that you can express this guy here as a conic combination of the other guys. Now, if you interpret things nicely, then you see that, okay, you have like these constraints, they imply a proof that C transpose X is greater or equal than the lower bound, and you're done. So that's the idea. Okay. Now the thing is that, okay, if the norm is just small and not zero, does it still work? And yes, it works. Yeah, we can do this. So to give you an intuition, so suppose that this norm is small, okay, then what does it mean now? And now we see why we choose X star in that way, is now take any point in your polytope. Okay, now I want to tell you that, you know, we're close to the lower bound, the optimum is close to the lower bound. You bring this form into this homogenized space, you bring this point into this homogenized space, and now you look at the inner product of this point with P. Now P has a small norm. You can also bound the norm of this point because we assume everything is inside the capital R ball. So this is also small. So, okay, but what is this thing here? It's small, but what is it? I mean, if you write it out, it's just, well, it's this, right? And now if you look at the respective terms, I mean, this thing here, if you write it out, it's just the slack of that point with respect to that inequality. So that's non-negative. Okay, I mean, we really, this is why we came up with P and blah, 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 right? So you can drop this. So you see that, okay, the last term here is small, right? So I'm also wondering, what is this? So now this just means, okay, I mean, let's bring this guy to the left-hand side, and I told you it's not too small. So you really, you have a proof that, okay, whatever point you take, its objective value is not really greater than the lower bound. It's very simple, like no trick. Okay, good. And now I should tell you that, okay, so it's good that, so if you're in the situation that this norm of P is small, that's good, okay? So how do we achieve this? So why will it happen that the norm of P is small with our choices? And that's also easy. So why does the norm of P become small? It's very easy. So recall that, like, our point X star looks like this. Good. Now, during our algorithm, there are two possibilities, okay? First possibility is our point might be not feasible, okay? So we get a cut. Now, I claim that this cut will help us so that in the next iteration, we will decrease our norm significantly. And the reason is geometric, is very simple. It's the following. So, okay, we get a cut that is violated by our point X star. So let's again write this in terms of an inner product with like a more like our point P. Well, this simply means that if you treat our cut as this vector, and we take the inner product with P, this simply means that they have a negative inner product. So what does it mean to have a negative inner product? Well, let's look at the picture. I mean, that's our point P from before. So it's in the convex hull of the constraint vectors. In the next iteration, this guy will be also in the convex hull of the constraint vectors. So these two guys will be in the convex hull, so we will be definitely allowed to move here. Okay, so in the next iteration, we're at least as good as this point, and this point has a significantly smaller norm than our previous point. It's like 1 or 2 line proofs. It's very easy. Okay. Yes. So in the next iteration, the norm will drop significantly. Okay, and so we get the bound that I claimed. In the other case, if your point X star is feasible, you basically do the same story with a little bit more care. You do the same argument with respect to this objective cutoff, which helps you to bring you closer to the origin. That's it. That's the full analysis, basically. And so this works. Good. Right. So 2 comments. I mean, I said that, okay, what's our method? I mean, find the minimum norm point in that polytope. And maybe you don't like this because this is too expensive. It turns out that if you just want to obtain this bound, you never need to compute the minimum. Like actually what you can do is you can do very cheap updates in the style that I just presented to you. It's just like you have this point that has a reasonable norm, you get a new point. Now on that line segment, you go to the point with the smallest norm. It's a very cheap thing that you can really do, and you immediately have this bound, okay? Now, of course, in practice, you want to, spend a little bit more effort. There's a trade-off what you can afford and how fast you want to converge. Good. Okay, yeah, I think there are some very interesting connections to multiplicative weights. Maybe there's some chance to discuss this later. Good, so let's do some computational results. I guess for most of us, it's our first computational paper, so we're very proud of this, although we are not experts. I think just for this project, I learned how to code in Julia. So we use Julia, and we use that jump package. So if you don't know this is a great interface to some of the solvers. Our implementations, I mean, we thought a lot about our implementations, and we really tried to make a very fair comparison. I cannot talk about all the details. What we do is we implement it all in very vanilla style. Like this cutting plane loop is just as you imagine, just write it down. Our method, in order to compute the minimum norm point, I take Gurobi. I just tell Gurobi, solve that formulation. I don't know what it does in the background. It's just working, okay? We have just chosen some more or less small epsilon, okay, that we want to hit. In all the experiments that you see, we have an iteration limit of 500, arbitrary, okay? And we also implemented, ellipsoid method is easy to implement. Analytic center, you have to be a bit more careful. We took straightforward textbook implementation. That's actually an implementation of Riley, which we just took, but it works. For us, so that's it, okay? And we tested our method on 3 very different types of instances. So the first thing is for people from combinatorial optimization. I mean, one standard example is the matching LP. So let's see how it performs, okay? So for the matching LP, I mean, I won't go into details, but like there are some initial constraints that we give to all the methods, and then there are these more interesting constraints, which are these guys. I mean, that's something that an oracle does for us. Okay, like standard Oracle, you search for a max odd cut and things work. Okay. Oh, I think I should. No, it's yeah. Anyway. Good. So one instance. So in the beginning, we tried some instances, and it turns out, okay, sometimes matching is really easy for an LP solver. So we thought about what is a nasty instance for this, and one nasty instance is, take an empty graph and place some random triangles somewhere. Now, what this method basically has to guess is these odd cut inequalities for all the triangles, more or less, to get a reasonable bound. So let's do this first, okay, random triangles. And then we see, so here what I do is I count the average number of iterations. I will also have a plot later to be a bit more fair, but what you see is, okay, the cut loop needs some time and we can do faster, which makes us happy, okay? It turns out that the ellipsoid method performs really bad. Now, I should also say that for analytic center, this number is not really fair. It really means that after 500 iterations, it's really not within the gap. Like it doesn't hit the gap. But I will tell you more about it on the next picture. So the situation is not that bad. Okay. But also, I mean, this is an artificial. Yes. Yes, okay, the question was, okay, good, yeah, makes sense. It's like, okay, I mean, like all these instances, they contain, I don't know, maybe like at most 75 random triangles. So in principle, the correct thing that you would do is for every such triangle, you put one constraint, right? This is the optimal way. It turns out that none of these methods realizes this. I mean, we are, let's say, close, but none of them is perfect. Yeah, so they output some other constraints, which, yeah, it's like we get all kinds of possible cuts, like, right? Yeah. Good. Now we also tested some more realistic instances. So this is a known benchmark set for coloring instances, and here we look even much better. We are happy about this. So this is great news. Okay. So one comment about, I mean, it's always a bit dangerous to just talk about average number of iterations, and I should be fair here. So what we see here, great. What we see here is a plot. obviously, about these methods, and you see two things. In the top here, you see the dual bound, how it behaves over time, and in the bottom, you see the primal bound, how it behaves over time. Okay. Now, what you see is the ellipsoid method is really bad. I mean, dual bound is very bad. Primal bound, well, it does something. This is all, of course, relative. The red thing, that's the cut loop. Okay, it works okay. So maybe I should switch to this. Cut loop is okay. You don't have a lower bound for cut loop because the cut loop doesn't offer you a lower bound. Okay. And now here, so the blue thing is our method. It converges much quicker. Okay. And here it's really within this tiny epsilon limit. For analytic center, the situation is not that bad. So the orange thing is analytic center. So the dual bound goes down. So that's nice. And also the upper bound, like the primal bound, it goes up, but, and this is the problem with analytic center, it really has trouble to close the gap. Like, I guess at this point, you should do something that also Andrea told you. At some point, you should really switch the method. So maybe at this point, just throw on the cutting plane method and you're already done. Maybe something like this, okay? So just to be fair, it's, okay, good. Another thing, we have also seen this, another natural instance, let's say if you go for SDPs, you can do this. So there is a nice instance we all like that comes from max cut, the max cut relaxation of Goomans and Williamson. So you have some nice linear initial constraints, but you also have this positive semi-definiteness constraints. We have seen how to separate this. That's exactly what we do, search for the most negative eigenvalue, blah, blah, blah. Here's just a simple test that, I mean, these instances are quite hard. We learned this. So here's just, okay, take 10 nodes, complete graph, so dense graph, and sample random weights. It gives you a nice instances, which are not that easy. Again, cut loop, we're a bit better, or at least in that order, whatever that means. Ellipsoid and analytic center still don't look very good. Here, like slightly more interesting things happen. The ellipsoid method can do something. Okay, analytic center is actually even better on the dual side in the beginning. Okay, but again, it cannot close the gap. I mean, we're all comparable, I would say, maybe a bit faster than cut loop, but I mean, that's good news, I think. Okay, and finally, I'm running out of time, so I will not talk about this in detail. So also machine learning offers some nice LPs that fall into this separation setting. If you want to know more, we can discuss it later. So they have some nice classification problems. We check these problems on some very famous machine learning repository. Here, I mean, the picture changes slightly. Now analytic center is a bit better than the cut loop, but I would say we are still in a similar order, which is, I guess that's still good news, okay? Good, so let me just close with some remark, like conclusion. So we have some nice iteration bound that we're at the moment happy with. Of course, this also works standalone. We don't need the cutting plane loop around this, so this still makes sense. Cheap updates suffice if you just want to go for this. We're happy at the moment with the experiments. I think there's a lot of flexibility to tune, and that's everything that I wanted to say. Thanks a lot.